Okay, so last time we showed that we could prove the Brouwer fixed point theorem if we assumed this basic theorem that said there's no way to map. So I'm tired of writing all this notation. So let's write for the closed ball centered at the origin of radius 1. Let's denote that by dn. So that's disk, right? So we've been talking about what's inside. Well, maybe we haven't used the word disk. We've talked about ball. Closed ball is often called a disk, and I'm tired of writing all this over and over and over again. So the theorem we stated on Friday was that there is no map, there's no smooth map, F, mapping the closed ball to its boundary, Sn minus 1. Right? The boundary of the closed ball is a sphere, but I'm going to write it as boundary just to be explicit. Right? This is a compact n manifold with boundary. The boundary is the n minus 1 sphere, which I think I've given you that notation before. The unit sphere in n dimensions. There is no smooth map F from the ball to its boundary with the property that every point on the boundary is left fixed. So every x that's on the boundary to start with stays where it is. Yes, Kate?
So what is if the boundary dn is Sn minus 1?
Yes.
Or Sn, so is that not a different dimension than the?
Well, shouldn't it be?
Well, then
If you
wouldn't
take the boundary of a disk in the plane, it's a circle.
Yeah.
It's a one manifold.
So it's not what space you're in. It's what.
It's the dimension of the manifold.
Is that belong to the boundary of the X belongs to the boundary?
Yeah. So I'm saying there's no way to take the closed ball, leave everybody on the boundary alone, leave everybody there fixed. So what I said on Friday was imagine clamping this piece of rubber that's in the shape of a ball, shape of a disc, clamp it on the edge like a drum head. And now your task is to take the rubber and in a continuous way push it all to the edge. Well, any fool knows you can't do it. Right? When you have this thing that's clamped on the edge and you try to push the rubber to the edge, you can't do it.
You can stretch the middle out.
I mean, you got to rip it and then you can do it. Well, if you rip it, it's not a continuous way of doing it. So we're going to prove it with the smooth there because we're doing everything with forms, but in fact it's true for continuous. If you hear the word, and I don't remember if it shows up in the book, such a map, but if you want to show off to your more advanced math major friends who know some topology, you can throw this word at them. Such a map is called a retraction.
Map from a set this to its boundary.
Well, from a set to a subset of this big set, that leaves the subset fixed. So this is saying there is no retraction from the disk to its boundary.
But there would be, all other retractions exist as long as they include the origin.
As long as they include an interior point. Well, not all.
There are retractions that exist outside the origin. Right? Outside the
For example, you can map the whole disk to a point, keeping the point fixed.
And it'd be like a
sink. Right?
That'd be a sink.
Well, if you think of that map as a vector valued function, no, it's only going to be a sink if
Well,
How can you map it all to a point?
Just the constant function.
Okay.
So the answer in general, Jonathan, is no, unless the point is the origin, I think.
Okay.
Otherwise, it's just a constant vector field.
Oh, but you're saying don't necessarily.
No, it's still not a sim.
You're saying don't fix the edge anymore.
No, right.
Okay,
Right,
that
right,
makes
right.
sense.
Just
Yeah.
map everything to that point.
Okay.
All right, so how are we going to prove this? Well, anytime you have a statement that says there isn't one of something,
Sure.
Assume there is.
Assume there, yeah.
got it by contradiction, right? And if I've told you that we're going to use Stokes' theorem to do it, you probably will have some way of figuring out the idea, although it's a little sneaky. So suppose we had such an F. And I'm telling you I want to think about Stokes' theorem. Well, you've got a boundary and you've got the whole thing. So Stokes' theorem somehow is sitting there if only you could figure out some k minus n minus 1 form. Some n minus 1 form let's say phi on the disk. And then I could conceivably apply Stokes' theorem by saying that integrating phi over the boundary of the disk is the integral of d phi over the disk.
This is a star-shaped region, right?
Very.
So we just have to find a closed form's exact. So
Well, no, I mean, I have to do this more specifically. So I want some n minus 1 form where this is going to give me a contradiction. Where this equality is a contradiction. So maybe, so I want some form on the disk where one integral here, for example, is 0 and the other one isn't. If I could get this wasn't 0 and this was 0, that would be a contradiction. So how am I going to use my f to create such a form on the disk?
Make FD something?
Now, f's a function.
Okay, yes.
What could you do if you have a function from one place to another? What can you do with forms? What we've been doing for months. You can do pullback. So the idea is going to be start with a form here, pull it back. That gives you a form on the disk. And that form phi should be the contradiction. So what form should I start with? So I want to start with an n minus 1 form on the boundary. What would be a good candidate for a form to start with on the boundary? Suppose it were 2 sphere. What 2 form could you think of writing down? The area 2 form.
So in the area.
And what would the area 2 form integrates to give you the surface area, which for sure is positive. So is there an analog of the area 2 form as an n minus 1 form on the n minus 1 sphere? Actually, I did something like this for you guys when we were doing the 4-dimensional Stokes theorem stuff. Can I think of a form that's going to be the analog of the area 2 form? Well, how did we get the area 2 form? We took the outward normal and turned it into a 2 form. If I have the unit sphere,
Well, if that's an n minus 1 form in n minus 1 dimensions, doesn't that mean you have to have a determinant?
well, so But remember how we arrived at our formula for the two form that worked for surfaces in R3? We used determinants, actually. So the analog to doing the n1 dx wedge dy, sorry, dy wedge dz plus n2 dz wedge dy plus n3 dx wedge dy, the analog of this sigma in R3 on a surface would be to do what? For my omega.
X dy.
Use the x vector as the coordinates here, because that's the normal to the unit sphere. But then we need, as we did when we proved Stokes theorem, we need some minus signs to make sure everything comes out right, right? There's some, what did I do here? This was a mistake. That's an x. Right, we wrote dz wedge dx rather than dx wedge dz here. So we need some minus signs. So we're going to have some minus signs where we leave out the ith dx and put the coefficient of the normal vector in the ith slot. The normal vector is x if we're on the unit sphere. So I'm claiming that omega has a non-zero, in fact positive integral over the n-1 sphere with the standard orientation on the n-1 sphere as the boundary of the ball. Well, what's the easiest way to compute the integral of omega? Rather than trying to parameterize, God help us, and pull back. Stokes theorem. After all, this is the boundary. So, what do I get when I take d omega?
That's 11.
You get n times n dv.
Is that right? So the point of putting the minus sign here is supposed to be that when I take dxi and I put it back where it belongs, I have to move it past I minus 1. We've been through this before. I have to move it past I minus 1 dx's. So that gives me that number of, with that sign, I can switch it over to this spot and I have a plus. So I'll have that happening n times here, because there's n terms here. I've left out 1 through n in each of the terms. That's n terms. Well, so as Cameron said, this is going to be n times the volume of the unit ball, and whatever that number is, I don't know the number off the top of my head, but that's for sure positive. Okay, so I have an omega with positive integral over the sphere. Now here comes the fun part.
And it would have a positive value over any
Sphere of any radius.
or any surface,
Or
because it's a
Well, by this argument, as long as that hypersurface is closed and bounds a region, you're going to get n times the volume of the region inside.
yeah.
That's right.
Okay.
But then it will not literally be the surface, it will not be the area form of that hypersurface.
Right, because it has a different out. It has its own normal.
And in fact, this isn't quite right. This isn't quite, well, actually, it is exactly the area form. So the volume form for that sphere.
Okay.
All right, what did we say we were going to do? Consider phi equal the pullback. So I started with a form here. I can pull it back, and I have a form now on the ball, on the whole disk. Now here's the tricky part. We use Stokes theorem here, but it sort of fooled you a bit. When I do the pullback, I'm thinking of this as a form not on Rn, but specifically on the sphere here. So I'm thinking of this as a differential form on the manifold rather than on Rn. What is d omega? Well, you're going to tell me we did this calculation. But that was thinking of omega as a form on Rn that we did this calculation. If I think of it as a form living just on the sphere, d omega is an n form on the n minus 1 dimensional sphere.
Which means something where we pulled back.
It doesn't change the quote-unquote domain of it.
So how many n forms are there on an n minus 1 dimensional manifold?
Only one.
Namely,
Zero.
0. So what's very confusing here is I've just done a calculation where I wrote down something that wasn't 0, but I'm saying if you think of this d omega as a form on the sphere, of course it's 0, because you can't, on an n minus 1 dimensional manifold, you can't have the wedge of n things other than 0. So this is just like the fact that we said lambda n of r n minus 1 star was 0. We said if you had more dx's wedged together than you had dimensions, you were going to get 0. So we actually made that case way back in the beginning of chapter 8. Okay, if you're buying this, then the proof is done. So we have the integral of phi over the boundary equals the integral of d phi over the whole disk. Now what's d phi? It's d of, whoops, sorry, it's d of the pullback of omega. And what do we know about d and pullback? They commute. So this is one of our crucial facts that we're going to use. This is the pullback of d omega, and we said as a form on the sphere, d omega is 0. So if you pull back 0, you get 0. Well, you might be wondering where we're going to use the hypotheses. We better use the hypotheses. What's this the same thing as? This is the integral of the pullback of omega on the boundary. Right, that's what phi is. But what on the boundary, what is f? If you pull
It's there.
omega back, so it's a form here, but you look at it only on the boundary back sitting in here. What do we know about f on the boundary?
The identity.
It's the identity. What's the pullback by the identity function? We haven't done that very often, but what's the pullback by the identity function? It's the same thing you had. So here, I'm using the fact that f is the identity function on the boundary. So what's the pullback? It's just omega. And what did we say the integral of omega was? Well, something that was positive. In particular, it's not 0. On the other hand, it is 0. Here's the contradiction. So everything would have worked perfectly okie dokie. There wouldn't be any contradiction to anything if I didn't have this step here. That pulling back by f was the same as having omega in the first place. In other words, if I didn't have a requirement that f had to be the identity on the boundary, I wouldn't get a contradiction. That's where the contradiction comes from.
So if it's not, if it's like a rotation or something,
If it's what?
if it's not the
If it's not the identity, all I've done is I've proved that this integral has to be 0. Right? So the contradiction comes at this last step where I put this in here. Everything here is correct. So if you didn't have that stipulation on f, you would prove correctly that the pullback of omega integrates to 0. And that wouldn't contradict anything.
We know what that's not equal 0, we know it's greater than 0, right?
Yeah. But all I care is that it's not 0 for this. So this actually takes students usually a month or so, or more than a month, in a graduate algebraic topology class. So you guys have got it for nothing out of Soakstone.
Why isn't there, how do we make that from, can you not just pull out? Oh wait, no, I can just pull back, my bad.
Right, it's pull back. Okay, so you're asked to give a slight generalization of this in your homework.
So if you remove any point on the disk and you said that point didn't have to follow the identity, that would actually...
Wait. You mean on the boundary?
Yes, on the boundary. And if you...
No, just removing one point, you aren't going to get away with anything. It's a continuous function. So if you allow your function f to have the property that pulling it back, you get cancellation. So if f does not wrap around the boundary the way the identity does, but it goes something like this, then you won't get a contradiction.
If
Because
it's just
it
like,
cannot wrap around,
if it's just like a rotation, then what's the?
then you still get a contradiction. You need an f that's going to have cancellation in it. It's sort of, if you think in 2 dimensions, you would need an f so that the image of this circle here under f has winding number 0 around the origin, and then you won't have a contradiction. So you would need this circle to map to something, some curve that doesn't wrap around, so it doesn't make a full circle, as it were. It goes around and then it ungoes around. If it does that, then you get no contradiction. And in fact, that's sort of where I'm headed next, a little bit here.
Why do we, the phi we found, the n-1 form,
Say what?
why do we, or what's the want, yeah.
Because I said what I wanted was a application of Stokes' theorem, which is what we did here. That was, right? So I was going to create a phi and apply Stokes' theorem, where the equality is a contradiction. And that's exactly what we have.
Okay. And the omega was just a way to get to that.
Right.
And prove that was contradiction.
Well, by pulling back the omega. So the key thing was to start with an n-1 form on the sphere whose integral wasn't 0. That's what I needed.
Okay.
So if we take an n form and it's okay to consider like an n-1 dimensional manifold and like that n form on that
Is 0. Yeah. Because if you feed in
even though
n-1 n vectors that are all tangent to your manifold, you're going to get determinant of some linearly limited set of vectors.
even if that we can, okay.
Yeah. You have to actually think about what it means to have a differential form literally on the submanifold. That means you're going to feed vectors into that form that are all tangent to the submanifold. All right, so I want to continue my exploration of ideas in topology a bit here. So, more ideas from topology here.
How old is the study of topology?
Old.
Very old.
I mean, in some ways it goes back to Poincaré, but some things go back further back. But, I mean, old compared to us. Not old compared to the Greeks.
200 years old? Older than that.
Depends where you're going, what you're going back to. Remember that rigorous analysis, notions of limits and continuity and sequences didn't come along till Cauchy in the 1800s. So we're past that a bit. All right, so I want to talk about the word homotopy. So a homotopy between two functions so I'm going to state this in sort of some generality here where I'm thinking of things basically as manifolds with boundary. So X is going to be a manifold with boundary. No, sorry, without boundary. Sorry. Without boundary. And Y is also going to be a manifold without boundary. So a homotopy between two functions is going to be a way of interpolating in a smooth way, like having a movie that starts at time 0 where you see the mapping f, and the movie runs, and at time 1 hour later, you see the map g. And everywhere in between, you saw some smooth map from x to y. So I'm going to give you the official definition. I'm going to draw some pictures. So a homotopy between two functions f and g is a smooth map, capital F, from x cross the time interval from 0 to 1 to y.
These are separate dimensions, x and y.
Yeah, they're living in, this is a k-dimensional manifold, this is an l-dimensional manifold. I mean, in applications we're going to do, they're going to be related typically. But I'm giving you the definition. There's a smooth map, capital F, so that at time 0, so when I put t equal to 0 here, I get f, and at time 1, I get g. So the way you can actually picture something like this as I said, is some sort of, you can think of a movie or you can think of a diagram like what I'm going to draw. Imagine that we had x was a circle. So I'm going to continue with my sphere notation. S1 is the set of unit vectors in R2. That's the unit circle. Okay. And let's say y is R3 minus the z-axis. So suppose f, mapping the circle into R3 minus the z-axis. What does this map from a circle into something look like? As you go around the circle, you go around something in this manifold, but you have to come back to where you started, right? Because you did on the circle. So, for example, I could take my circle, and there's my y now. I'm taking R3 minus the z-axis. So f is going to map me to what? It's going to take a circle, and it's going to give me some closed curve in R3 that misses the z-axis.
Oh, right, because it doesn't have to be surjective.
Oh, no.
I was
It's a
trying to
smooth map that to each point, so I start here, I don't want to use the same color. I'll start here, and I'll be somewhere in R3 minus the z-axis. You're an ant, you start walking around the circle. Well, you start moving in R3, but you never hit the z-axis. So you come around, and you do whatever you feel like doing, but eventually when you come back, you've closed the curve up. So a map from the circle to y is a closed curve, smooth closed curve in R3 minus.
Could it possibly fill up R3 minus the z-axis?
You did a challenge problem back in the first week. Any C1 map has to give you something that has volume 0.
Okay, that makes sense.
So, here's G. G, so this is, my green thing is a picture of F. My yellow thing is going to be a picture of G. G is just going to take a loop and go once around the z-axis like this.
And she goes from,
Still a map from the circle. to R3 minus the z-axis. It just goes, loops around in a nice flat circlish curve. Still going, so it comes out in front here of the z-axis, goes back behind it there. Do you think there's a homotopy between f and g?
Yeah, sure.
I can kind of see it.
So what are you thinking of doing when you do this homotopy? You're thinking of actually deforming the curve as the movie runs. You start, say, at time 0 with this, and as time starts happening, you undo this loop-de-loop here, and you start sliding things more so it looks like a circle, and then you start sliding it down, and at time 1 you're there.
There's always.
Can you picture that?
Mm-hmm.
You could even do it pictorially by saying, look, I'm going to draw something that's not quite as complicated as that curve there. I'm going to draw something like this for my green curve, and something like this for my yellow curve, and you could imagine making a vacuum cleaner hose that joined them up. Why I picked a vacuum cleaner hose, I'm not exactly sure.
Could use the copper filter.
Did some spring cleaning done this weekend.
So what am I doing? I'm making a hose that's stretchable, and at the bottom it's got this loop, at the top it's got a loop, and then I just deform the top because it's a stretchable hose. So the homotopy basically is saying run the movie so that this is t equals 1, this is t equals 0, and in between, at time intermediate value t, I'd see some curve like that. Mm-hmm.
If the yellow circle G had the opposite orientation, would it not work because of the axis?
Couldn't do it, could you? And actually, I'm going to ask a very similar question in a minute. Dennis?
So I kind of think this is going to lead into deforming the torus. It's lead something into
Not necessarily the torus, but it is leading
something
somewhere.
akin to that.
It's important that that green curve goes behind it.
This is related to knots. It's also related, if you've looked at your homework problems, there's a picture in the book that looks pretty weird. It's related to that
So
problem.
it's important that that green curve goes behind that blue line.
Say again?
It's important that that green curve looks like it goes behind that blue line.
Right. In fact, that's exactly the question I'm going to raise now, if I ever get a chance.
So between T0 and T1, it cannot cross the z-axis in this case.
All the mappings have to map to y, so you can never hit the z-axis. That's crucial. So now I'm exactly going to raise the question that you all are thinking about. Suppose my two curves looked, instead of as they do, suppose my yellow curve still looks like this, my green curve looks like this. Can you make a homotopy between the map of the circle to this and the map of the circle to this, where the homotopy again is mappings to y, so you're never allowed to cross the z-axis?
No, it'd be a magic trick.
What does this remind you of?
The arithmetic checks.
Yeah, it reminds you of this sort of thing we were doing here somehow.
It's like pulling a ring off
crossing
the
the
iron.
y with the x.
So how do you rigorously prove that you can't ever do it? Of course it's obvious, but how do you give a proof? Somehow we got to be using the machinery we got. So what you guys are conjecturing here,
Can we use
that if f, quote, wraps around the z-axis, and g does not, I guess I got that backwards, but it doesn't matter. They cannot be homotopic maps. Yes, Ken?
or can we like project it and use that the wrapping thing?
Yeah, there you go. So Ken's got the right intuition. Remember our famous one form that told you when you wound around the origin?
Is it, they cannot be homotopic maps, or you cannot draw homotopic maps?
No, they're not. There can't be such a capital F. My picture is representing how you can think of an F by filling in the surface and then saying you can create a mapping that does that, where you think of the movie running from time 0 to time 1. But it's whether I can draw it or not, there's not a homotopy.
How would we write this conjecture if it was R3 minus Y to Z or something like that? Or something
Write the
like
same thing,
Okay.
but, I mean, are you
Well, is there like a general way we can write Z-axis?
a line? Mm-hmm.
So you would have to use the winding function so that you would have to make an argument that if G ever crossed the Z-axis, you would have a discontinuous function. Like it would suddenly spike from 0 to 4 pi.
You're on the right track. You're exactly on the right, except it's 2 pi. Right? So this one form made sense in R2 minus 0. I can now think of it as a form in R3 minus the z-axis. Right? It's defined everywhere except where x squared plus y squared is 0, which is what in R3? It's the z-axis. So this thing, analogous to the fact that in the plane it didn't make sense at the origin, when I think about projecting, which one of you, somebody mentioned that word, projecting R3 to R2, what projects to the point at the origin is exactly the z-axis. So I'm taking this, if you want to think of it that way, I'm taking this one form on R2 minus the origin and pulling it back to R3 minus the z-axis. But officially, you can just write it down and it makes sense with no z's in there. What do we know about this one form?
It's closed but not exact.
Closed, but not exact. Well, so I'm going to state a proposition which should apply to this case. Proposition. Suppose X is a compact k-dimensional manifold so this X here is a compact oriented k-dimensional manifold. Y is a compact manifold and omega is a k-form on Y that's closed. You see where I'm heading with this? Here's my Y. Here's my Y, and here's a closed one form on Y. What am I going to do with it? I'm going to pull it back to my X, and then I'll have a one form on the circle. What the proposition is going to say is, if F is a homotopy between two maps, just as I set it up in the definition here, I put arrows on my F's here, I guess, well, but whatever. I'm tired of writing arrows everywhere. If you have a homotopy between little f and little g, then guess what? Pulling back my omega and integrating it over x, I can do it by either function. And what do you think I'm going to get? If you can smoothly deform one map to the other, and you had this one form, you could integrate here, or you could integrate it here, what do you guys think should be true?
It should be equal.
They should be equal. How would you prove that? Well, in this picture, you would think about integrating omega on this curve. Integrating omega on this curve. What can you tell me about?
Is this also why the orientation has to be correct, or else it would be negative?
Yes, very good. So what have you got here? Well, you've basically got a cylinder. And we went through this, I think, back when we were doing surfaces. If you take maybe we didn't do this actually. If you take a cylinder, which officially is a circle cross an interval, what's the boundary of that?
It's two circles.
It's these two circles, right? But if you orient the circle, do you get the same orientation on top and bottom when you do the boundary of the cylinder?
I think so. Let's see.
So imagine,
No, you don't.
Because when you flip it upside down,
No, because you have to have an outside pointing normal.
right, imagine you orient your circle here, this way. That means I'm walking around this way on the bottom circle as you look at it, right? You're going counterclockwise around. That means you're walking this way, and then I roll it up and it's counterclockwise. I walk around, I walk around, I walk around, I walk around. What happened? Which direction did I go on this piece? Opposite. So if you're going this way on this circle, you're going the opposite way on the upper circle.
That's not what's happening with our weird coffee filter thing, though. You're not reversing.
Well, hang on. So what happens when you, so what's the proof of this proposition? Here's the proof. So what I'm saying here is that if I take the boundary of x cross I, cross the interval 0, 1, I'm getting up to a question of sign, the upper one minus the lower one. Or I might get the minus the upper one plus the lower one. But they have opposite signs on them. That's what we just observed here. And if you actually take the rigorous definition I've given you of how you do orientation, it's going to work in general. But the circle you go around on the bottom, and the circle you go around on the top, you go in opposite directions. So the boundary has opposite signs when you look at those two pieces. So you can check this carefully with our definitions. What's the proof of the proposition? If I take the integral of the pullback of omega by f, and I subtract the pullback, well, let's say by g, I'll be consistent with this, and I subtract the pullback by f, this is meaning that I can think of integrating over the top slice, when t is 1, the pullback by the homotopy. And here I can take the pullback by the homotopy on the bottom slice. Why is that? Why is capital F, when I'm on the time 1 slice, the same as g? Well, that's this. When I am on that top copy of x, when t is 1, the homotopy is g. And when I'm on the bottom one, the homotopy is little f. But now, what are you going to do next? So this difference is up to a sign anyway.
So
The same as pulling back and integrating over the boundary.
Stokes theorem.
By Stokes' theorem, that means it's plus or minus the integral over the whole thing of d of it. What is D of the pullback?
So,
Pullback of the D, which is 0 because
close.
omega was assumed closed. What do we conclude? We conclude that the integral of f pullback and the integral of g pullback are the same. So, what's the official answer to this question? If you pull back this one form by this map, you're just integrating this one form around a curve that doesn't go through the origin in the xy plane, or doesn't go around the origin. So what do you get? When you pull back and integrate this one?
0.
0.
Oh.
And this one?
2 pi.
2 pi. Therefore,
2 pi equals 0, so.
2 pi not being equal to 0 means they couldn't be homotopic maps that gave you those two curves. So, integral of f pullback of my omega over the circle. I didn't say which was which. The yellow one is G. And the green one is F. There's no homotopy between them. So you have a fun problem for which I encourage you to get out your modeling clay or pipe cleaners or whatever physical models you want to build. If you look at the problem in the book, it has these weird curves, and it's asking you to compute some integrals. You're going to have to apply principles like this. So it's a good exercise in geometric imagination. What I'm going to do tomorrow is two things. So tomorrow, we're going to do two very cool applications of this before we go on to the last part of the course, which is back to linear algebra, so you can breathe again for the end. Tomorrow we're going to talk about the fundamental theorem of algebra. How many people besides Haley know what this is? So I'm going to show you how you can count roots of polynomials by applying what we're talking about here today. So this is a two-dimensional version of Gauss's theorem. And then I'm going to prove the Harry-Ball theorem, which is another example of an application of a homotopy I did to prove that you can't comb the hairs on a sphere of dimension. So you're getting a lot of bang for your buck out of Stokes' theorem here. Okay.